Okay, let's imagine we have a new type of integral that we encounter. So let me start with an example here. Say we see this integral, the integral of x times cosine x dx. So I don't think a substitution will work here because if it was cosine of x squared, that might be helpful because the x outside is the derivative of x squared, and something like that could help. But here, this is just two different types of functions multiplied together. One is like just a linear function, and one's a trigonometric function, right? X times cosine x. So that's the first thing I just want to note is that this is like two different types of functions multiplied together. And where it's not the nice substitution situation where you have the one type is the derivative of the inside of the other type. That makes sense. Okay, so I just want to make a note of that because this is its when we encounter this sort of thing, that's going to be the technique a lot is going to be this thing called integration by parts. Lost what I was writing here. Two different types of functions multiplied together. Okay, so as often we do when we first encounter a new type of integral, let's try to guess an answer and differentiate it and see what works. So guess, and I think a pretty natural guess here is just x sine x. Because we know that the derivative of sine is cosine and the antiderivative of cosine is sine. Thus, maybe x sine x is in the answer at least. So check. Let's differentiate x sine x. And then we can sort of see immediately why this won't quite be the right answer yet because of the product rule, right? The derivative of x sine x is not x cosine x. It's first times the derivative of the second, which is x cosine x. That is the x cosine x. But you also have to do plus the second times the derivative of the first. So that's sine x times 1. Right? And so that's just sine x. So we're close. But we're off by this sine x term here. Right? Okay, but it's just an added term, so maybe we can get rid of it. Like there's a way that maybe if we adjust our guess, right? So idea, add something to our guess that when differentiated, like when we take the derivative, right? When we actually take the derivative, when we take the derivative, we'll cancel out the sine x. Right, there's this extra sine x term we don't want. Maybe we can add something to our guess that will cancel it out. Hopefully that seems like a reasonable idea. Let me just be a little more abstract about it because this helps us maybe figure out what we should add. In other words, the new guess will be x sine x plus some function, f of x, where f prime of x, because we have to differentiate it, right? When we check, we differentiate it, should be negative sine x so that that will cancel out, right? So that this right here will cancel out that. Right, if that's because when we differentiated this, we got this. And then if we add the derivative of this, that should be minus sine x to cancel out the sine x. Okay, so that's a good idea. And then from there, we can just say, well, we can actually figure out what that is, right? Because f of x then is really going to be the integral. Actually, it's negative the integral of sine x. I'm putting the minus sign outside because I'm thinking of this term, this sine x, being the thing that we want to get rid of after differentiating. So it's negative sine x, which is negative cosine x, right? The antiderivative of sine is negative cosine, so that's just cosine x. I guess I should put a plus c here, but I can always just put the plus c at the end. Okay, so there you go. So that's the thing we want to add to our guess. But I just want you to keep in mind that this is kind of it's almost like we can make a formula for what we need to change our guess by. It's sort of the negative, the integral of the thing that we want to get rid of. Should I write that in words? This is negative the integral of the thing we want to get rid of. And there's a beeping in the background. I don't know if you can hear it, but it's annoying. Sorry, a truck was backing up outside with the beeping. It's really annoying. It's probably going to happen again. I paused the video until it went away. Might pause the video again if it happens again. Okay, so this is where we were, right? We said this is okay. So we have our new guess. So our second correct guess, we know this is going to work. Is that the integral of x cosine x is going to be x sine x. It's going to be up here. It's going to be this x sine x plus this function, which we figured out is cosine. So x sine x plus cosine x plus c. Okay, so that's kind of nice. We figured out a formula. Or we figured out a way to anti-differentiate this by fixing our guess. Now, that's a motivating example because I want to generalize this idea and use, derive this formula, this integration by parts formula, come up with this integration by parts formula. So if you think about what we did, we used the product rule, right? Because at some point up here, this was the product rule, is how we got this derivative. And this was our original integral. This is the term we had to get rid of. So I just want to keep all that in mind. So go down here and say we use the product rule. So let me just write out the product rule. So that is the derivative of u times v. If we have two functions multiplied together, u and v, it's the first times the derivative of the second plus the second times the derivative of the first, right? And the other thing is when we have integrals, we have the dx, the du, the dv, we have all those floating around. And so there's this other, we can sort of think about canceling the dx's, getting rid of the dx's. And there's a word for this, it's called differential notation. So, or in quote, differential notation, the dx in an integral is sometimes called a differential. If we get rid of the dx's, we could write it as you think of it as the derivative of uv is u times the derivative of v plus v times the derivative of u, right? So in our example that we had, right, in our example, we had the derivative of x sine x was x cosine x plus sine x times 1, right? That's u is x. Well, okay, so something is going on here. Oh, I'm not writing this correctly. sorry, I need to be careful about this term right here. And because there's d's, so that whenever there's d's, there should be dx's, like dv. It's like we did in u substitution, right? When we had u equals, if u is sine x or v is sine x, then dv should be cosine x dx. So let me be a little more careful here. Just gonna erase this and try it again. So in our example, we had d of x sine x. And according to this formula, it's x times d of sine x plus sine x times dx. And then the question is, what is d of sine x? D of sine x is the derivative of cosine x, but then you throw in the dx. It's like we did, again, like when we did use substitutions, we kind of the same thing, right? So the formula that I get is, let me just write this out again. D of x sine x is x cosine x dx plus sine x dx. And here's the idea. This is a derivative of x sine x. So when we integrate this, the d would go away. So I want to integrate both sides. So then if we do that, I guess what I'm saying is the integral of d, right? The integral of d of x sine x is really just x sine x. Right, that's what this term becomes when we integrate. And then on the right, we get two integrals. So I integrate the whole right side, but because of this plus sign, I can just integrate each term. Plus the, yeah, like this, right? And now if you notice, this right here is the integral we want to find. We wanted to find. This right here was our guess, our first guess. And this right here is the thing we need to get to cancel, right? The thing we want to use to cancel. A sort of canceling term. But it's an easier integral. So in fact, this becomes, I'm doing the same example again, but I'm just showing you how it works in this framework. That we get x sine x equals the integral of x cosine x dx plus, well, this is a minus cosine x, right? The integral of sine is minus cosine. And then we move this over to the other side, and that's how we get our answer. And then we throw the plus c in at the end. Right, so this is how we get, if I add cosine x to both sides, the cosine x will end up over here, and then I get the plus c, right? And now I want to generalize this to a fully general formula using, in terms of u's and v's, right? Like when we went up here, we had this, right? And I want to integrate that instead of integrating this, which we did for this example. So let's generalize. Right, so we start with our formula d of u times v is u times dv plus v times du, and we integrate both sides. And when we integrate the d, it goes away, so we just get u times v. And then we integrate each of these terms, because of the plus sign, we can just integrate each of those terms separately. So that's the integral of u dv plus the integral of v du. And this is the general, well, actually, okay, so then we have to subtract, that's almost the general formula. Then we subtract this over to the other side, and so we get the integral of u dv is u times v minus the integral of v times du. And that's the general integration by parts formula. Right, and again, just comparing to the example up here, yeah, it's like this is, u is right here, this is dv. So this is the integral that we started with in the example, right? And the idea is recognizing that we have one function times another, but the other we want to think is the derivative of something because we're going to end up integrating it, anti-differentiating it to get the sign there. And then that's v. This is u again. And then the cosine is the, we have v du. The integral of v du. Actually, I should do it up here. Sorry. This is u. I guess I did the integral first. Yeah. Sorry. This is u and this is v. This is u. This is du. This is dv. The whole thing here is dv. It's supposed to be a v. And this is v again. Okay. So that's the same. That's the form. That's where we're using these. And just to write it even just one more time, the idea is that we identified u to be x, dv to be cosine x dx. And then we differentiate this and we get du is dx, and we integrate this one and we get v is sine x. And then, so here, right, when we put, this was our original integral, the u dv integral was our original integral. U times v is easy enough. That goes there. And then the integral v du is this. So the integral of v du in this case is the integral of sine x dx, which is easier, which was the point. We get an easier integral. And so we've transformed a harder integral into an easier integral by this method of integration by parts. So while in the next video, I'll just do a bunch of examples just to show you how it works. I'll stop there.